A neutral conductor is required on a three-phase service even if there are only three-phase motors connected and there is no load in the neutral. According to the National Electrical Code, a neutral conductor is required for several important reasons. Firstly, grounding is essential for safety. The neutral conductor provides a path for grounding the electrical system. Grounding helps to protect people and equipment from electrical shocks and electrical fires. Secondly, voltage balancing is another crucial function. The neutral conductor helps to balance the voltage between the three phases. This is important for ensuring that motors and other equipment operate properly. Thirdly, fault protection is also a critical aspect. The neutral conductor provides a path for fault currents to flow back to the source. This helps to protect the equipment from damage and prevents electrical fires. Therefore, even if there is no load in the neutral, a neutral conductor is still required on a three-phase service. It's important to elaborate on each of these reasons to fully understand the necessity of a neutral conductor in a three-phase system. Let's begin with grounding. Grounding in an electrical system refers to intentionally creating a low resistance path to the earth. This path allows fault currents to flow safely back to the source, tripping a circuit breaker or fuse and disconnecting the circuit. Without a proper grounding system, a fault current could energize metal parts of equipment, creating a shock hazard. The neutral conductor plays a vital role in this grounding system. It is typically bonded to the grounding electrode conductor at the service entrance, establishing a direct connection to earth. This connection ensures that any fault current has a clear path to ground, minimizing the risk of electrical shock. Now, let's discuss voltage balancing. In a balanced three-phase system, the voltage between each phase and neutral should be equal. However, in reality, loads are often not perfectly balanced. This can cause voltage imbalances, which can lead to several problems. For example, voltage imbalances can cause motors to overheat, reduce their efficiency, and shorten their lifespan. They can also cause sensitive electronic equipment to malfunction. The neutral conductor helps to mitigate voltage imbalances by providing a return path for unbalanced currents. This helps to keep the voltage between each phase and neutral more consistent, improving the performance and reliability of the electrical system. Finally, let's consider fault protection. A fault current is an unintended current that flows through an abnormal path, such as a short circuit or ground fault. Fault currents can be very high and can quickly damage equipment or start a fire. The neutral conductor provides a low impedance path for fault currents to flow back to the source. This allows overcurrent protection devices, such as circuit breakers and fuses, to quickly detect and interrupt the fault current, preventing damage to equipment and reducing the risk of electrical fires. In summary, the neutral conductor is a critical component of a three-phase electrical system, even when only three-phase motors are connected. It provides essential functions for grounding, voltage balancing, and fault protection. Ignoring the requirement for a neutral conductor can create serious safety hazards and compromise the performance and reliability of the electrical system. The National Electrical Code mandates the use of a neutral conductor in most three-phase services to ensure the safe and efficient operation of electrical equipment. The specific requirements for the neutral conductor, such as its size and installation methods, are detailed in the NEC and should be carefully followed. For example, the NEC specifies the minimum size of the neutral conductor based on the size of the phase conductors and the type of load being served. It also specifies the methods for grounding the neutral conductor and bonding it to the equipment grounding system. It's important to consult the NEC and other applicable standards to ensure that the neutral conductor is properly installed and maintained. In addition to the NEC requirements, there may be local codes and regulations that also apply. It's important to check with the local electrical inspector to ensure that all applicable requirements are met. Failing to comply with these requirements can result in fines, penalties, and even the shutdown of the electrical system. Therefore, it's essential to take the requirement for a neutral conductor seriously and to ensure that it is properly installed and maintained. Let's dive deeper into the specific NEC articles that address the neutral conductor requirements. While a comprehensive review of the NEC is beyond the scope here, highlighting key sections can provide a better understanding of the code's intent. NEC Article 250 covers grounding and bonding. This article outlines the general requirements for grounding electrical systems, including the neutral conductor. It specifies how the neutral conductor must be connected to the grounding electrode system and how it must be bonded to the equipment grounding conductors. Understanding Article 250 is crucial for ensuring that the grounding system is properly installed and that the neutral conductor is effectively grounded. NEC Article 220 covers branch circuit, feeder, and service calculations. This article provides the rules for calculating the size of conductors, including the neutral conductor. It specifies how to determine the neutral load based on the type of loads being served and the phase balance. Accurately calculating the neutral load is essential for selecting the correct size conductor and ensuring that it can safely carry the expected current. NEC Article 310 covers conductors for general wiring. This article provides information on the types of conductors that are permitted for use in electrical systems, including the neutral conductor. It specifies the ampacity of different conductor sizes and types and provides guidance on directing conductors for ambient temperature and other factors. Selecting the appropriate conductor type and size is crucial for ensuring that the neutral conductor can safely carry the expected current and that it is suitable for the intended application. These are just a few of the NEC articles that are relevant to the neutral conductor. It's important to consult the NEC in its entirety and to understand all of the applicable requirements. In addition to the NEC, there may be other standards and guidelines that are also relevant. For example, the National Electrical Manufacturers Association provides guidance in the selection and installation of electrical equipment, including neutral conductors. The Institute of Electrical and Electronics Engineers publishes standards on power quality and grounding, which can also be helpful in understanding the requirements for neutral conductors. Consulting these additional sources can provide a more comprehensive understanding of the requirements for neutral conductors and can help to ensure that the electrical system is properly designed and installed. Let's address some common misconceptions about neutral conductors and three-phase systems. One common misconception is that the neutral conductor is not needed if the load is balanced. While it's true that a perfectly balanced load will not have any current flowing in the neutral conductor, it's rare to find a perfectly balanced load in the real world. Even small imbalances can cause current to flow in the neutral conductor, and this current can overload the conductor if it's not properly sized. Another common misconception is that the neutral conductor is only needed for single-phase loads. While it's true that the neutral conductor is essential for providing a return path for single-phase loads, it's also important for three-phase loads. As mentioned earlier, the neutral conductor helps to balance the voltage between the phases and provides a path for fault currents to flow back to the source. Even if there are no single-phase loads connected, the neutral conductor is still needed for these reasons. Another misconception is that the neutral conductor can be smaller than the phase conductors. While this may be true in some cases, it's not always the case. The NEC specifies the minimum size of the neutral conductor based on the size of the phase conductors and the type of load being served. In some cases, the neutral conductor may need to be the same size as the phase conductors or even larger. For example, if the load is nonlinear, such as electronic equipment, the neutral conductor may need to be oversized to handle the harmonic currents that are generated. Finally, it's a misconception that the neutral conductor is only needed at the service entrance. While it's true that the neutral conductor is typically grounded at the service entrance, it's also important to provide a neutral conductor throughout the electrical system. This ensures that there is a return path for imbalanced currents and that the voltage is properly balanced throughout the system. In summary, it's important to understand the true requirements for neutral conductors in three-phase systems and to avoid these common misconceptions. The NEC provides detailed guidance in the selection and installation of neutral conductors, and it's essential to follow these requirements to ensure the safe and efficient operation of the electrical system. Let's consider some practical examples of how the neutral conductor is used in three-phase motor applications. In a typical three-phase motor installation, the motor is connected to the three-phase power supply through a disconnect switch or circuit breaker. The neutral conductor is connected to the motor's frame, providing a ground path for fault currents. If a fault occurs within the motor, such as a short circuit to the frame, the fault current will flow through the neutral conductor back to the source, tripping the circuit breaker or blowing the fuse. This protects the motor from damage and prevents electrical shock. In some cases, the motor may also be connected to a variable frequency drive, which controls the motor's speed and torque. The variable frequency drive may also require a neutral connection for its control circuitry. The neutral conductor provides a stable reference voltage for the control circuitry and helps to prevent electrical noise from interfering with the drive's operation. In addition, the neutral conductor may be used to provide power to auxiliary equipment associated with the motor, such as cooling fans or control panels. This allows the auxiliary equipment to be powered from the same source as the motor, simplifying the wiring and reducing the risk of voltage imbalances. It's important to note that the specific requirements for the neutral conductor in a three-phase motor application will depend on the type of motor, the type of drive, and the type of auxiliary equipment being used. It's essential to consult the manufacturer's instructions and the NEC to ensure that the neutral conductor is properly installed and connected. Furthermore, let's discuss the implications of removing or improperly installing a neutral conductor in a three-phase system. Removing or improperly installing a neutral conductor can have serious consequences, including equipment damage, electrical shock, and fire. Without a neutral conductor, the voltage between the phases can become unbalanced, which can damage motors and other equipment. The unbalanced voltage can also cause excessive current to flow in the phase conductors, which can overheat and damage the insulation. This can lead to a short circuit or ground fault, which can cause a fire. In addition, without a neutral conductor, there is no ground path for fault currents. This means that if a fault occurs, the metal parts of equipment can become energized, creating a shock hazard. Anyone who touches the energized equipment can receive a serious or even fatal electrical shock. Improperly installing a neutral conductor can also have serious consequences. For example, if the neutral conductor is not properly sized, it can overheat and melt, causing a fire. If the neutral conductor is not properly grounded, it can become energized, creating a shock hazard. It's essential to take the installation of the neutral conductor seriously and to ensure that it is properly sized, grounded, and connected. Only qualified electricians should perform electrical work, including the installation of neutral conductors. Qualified electricians have the knowledge, skills, and experience to perform electrical work safely and correctly. They are also familiar with the NEC and other applicable standards. Attempting to perform electrical work without the proper qualifications can be dangerous and can lead to serious consequences. Let's consider some specific scenarios where a missing or improperly installed neutral conductor can cause problems. Scenario 1 involves a three-phase motor connected to a system without a neutral. If one of the phase windings in the motor develops a short to ground, the fault current will have no path back to the source. This means that the circuit breaker will not trip and the motor frame will become energized. Anyone who touches the motor frame will be exposed to a dangerous electrical shock. Scenario 2 involves a three-phase panel board with single-phase loads connected. If the neutral conductor is missing or undersized, the voltage to the single-phase loads will become unbalanced. This can cause the lights to flicker, the appliances to malfunction, and the electronic equipment to be damaged. Scenario 3 involves a three-phase generator connected to a system without a neutral. If the load and the generator is unbalanced, the voltage between the phases will become unbalanced. This can damage the generator and the equipment that is connected to it. In each of these scenarios, the absence or improper installation of the neutral conductor can create serious problems. It's essential to ensure that the neutral conductor is properly installed and maintained to prevent these problems from occurring. To further illustrate the importance of the neutral conductor, let's discuss some advanced concepts related to neutral current and harmonic distortion. In a purely linear three-phase system with a perfectly balanced load, the neutral current should theoretically be zero. However, in reality, most electrical systems have some degree of imbalance and non-linear loads, which can cause current to flow in the neutral conductor. Nonlinear loads, such as electronic equipment, generate harmonic currents. Harmonic currents are currents that have frequencies that are multiples of the fundamental frequency of the power system, which is typically 60 Hz. These harmonic currents can flow in the neutral conductor and can cause it to overheat. In some cases, the harmonic currents in the neutral conductor can be greater than the current in the phase conductors. This can require the neutral conductor to be oversized to handle the increased current. In addition, harmonic currents can cause voltage distortion, which can damage sensitive electronic equipment. To mitigate the effects of harmonic currents, it's important to use harmonic filters and to properly size the neutral conductor. Harmonic filters are devices that are designed to reduce the amount of harmonic current that flows in the electrical system. Properly sizing the neutral conductor can ensure that it can safely carry the harmonic currents without overheating. Furthermore, let's consider the role of the neutral conductor in different types of three-phase systems, such as Y and delta systems. In a Y system, the neutral conductor is connected to the center point of the Y, which is also the ground point. The neutral conductor provides a stable reference voltage for the system and helps to balance the voltage between the phases. In a delta system, there is no neutral conductor. Instead, one of the phase conductors is typically grounded. While delta systems can be more efficient than Y systems in some applications, they are also more susceptible to voltage imbalances and harmonic distortion. For this reason, Y systems are generally preferred for applications where voltage stability and power quality are important. In summary, the neutral conductor plays a vital role in three-phase electrical systems. It provides essential functions for grounding, voltage balancing, fault protection, and harmonic mitigation. Ignoring the requirement for a neutral conductor can create serious safety hazards and compromise the performance and reliability of the electrical system. It's essential to consult the NEC and other applicable standards to ensure that the neutral conductor is properly installed and maintained. Let's conclude by reiterating the key takeaways regarding neutral conductors in three-phase systems. Firstly, a neutral conductor is required on a three-phase service, even if there are only three-phase motors connected and there is no load in the neutral. Secondly, the neutral conductor provides essential functions for grounding, voltage balancing, fault protection, and harmonic mitigation. Thirdly, the NEC provides detailed guidance on the selection and installation of neutral conductors, and it's essential to follow these requirements to ensure the safe and efficient operation of the electrical system. Fourthly, removing or improperly installing a neutral conductor can have serious consequences, including equipment damage, electrical shock, and fire. Fifthly, only qualified electricians should perform electrical work, including the installation of neutral conductors. By understanding these key takeaways, you can help to ensure that three-phase electrical systems are properly designed, installed, and maintained, promoting safety and reliability.